The information provided in this video is for educational and entertainment purposes only. Automotive repair, especially involving modern high-voltage electrical systems, internal combustion engines, and heavy machinery, carries inherent risks of physical injury, property damage, and legal liability. This content does not constitute professional advice, nor does it replace formal certification or training from accredited institutions. The 3D and augmented reality technologies discussed are evolving, and their application may vary based on manufacturer specifications and local regulations. Viewers are strongly encouraged to conduct their own due diligence, consult official service manuals, and seek guidance from qualified professionals before attempting any repairs or investing in training programs. The creator of this video is not responsible for any actions taken by viewers based on this content. In a small, dimly lit independent garage in the outskirts of Chicago, a master technician with 40 years of experience recently walked away from his toolbox, looked at a 2024 luxury electric SUV, and realized he was effectively illiterate. This man could rebuild a transmission blindfolded. He could diagnose a vacuum leak by the scent of the exhaust. But as he stared at a vehicle containing over 100 million lines of code and a battery architecture that could deliver a lethal arc of electricity in milliseconds, he realized the era of the wrench was being superseded by the era of the spatial interface. We are currently witnessing a silent collapse in the American automotive sector. There is a documented shortage of over 600,000 technicians across the United States. Historical trends indicate that as vehicles become moving supercomputers, the traditional method of learning, shadowing a senior tech for 5 years while getting grease under your fingernails, is no longer just slow. It is becoming obsolete. The complexity of modern vehicle architecture has outpaced the human capacity for traditional rote memorization. Imagine standing in front of a complex engine bay where every single component is shrouded in plastic covers and thermal shielding. To the naked eye, it is a black box. But then you slide on a pair of high-resolution mixed reality goggles. Suddenly, the car becomes translucent. You see a digital twin of the cooling system glowing in a neon blue overlay. You see the exact torque specifications for a hidden manifold bolt hovering in three-dimensional space, right next to the physical part. As you reach out, a haptic sensor in your glove pulses, telling you that you are 3 millimeters away from the correct sensor. This is not science fiction. This is the current reality of 3D auto repair training, a shift that is fundamentally retooling how the American workforce interacts with machines. For the average viewer, the problem today is simple but devastating. Car repairs are becoming exponentially more expensive because the labor required to diagnose them is becoming scarcer and more specialized. A simple sensor failure that used to take 20 minutes to find now requires a $3,000 diagnostic suite and a technician who understands data packets as well as they understand gear ratios. This video serves as a deep dive masterclass into how 3D training platforms are solving this crisis by reducing the time to competency for new mechanics by as much as 70%. The US audience is currently facing a repairability wall. When your vehicle breaks down, you are often at the mercy of a dealership because the local independent shop lacks the training to handle the proprietary 3D map systems of a modern vehicle. This creates a bottleneck that drives up insurance premiums and total cost of ownership. We are going to explore how spatial computing is democratizing this high-level knowledge. We will look at case studies from major manufacturers who are ditching 500-page paper manuals for interactive 3D modules that allow a trainee to explode an engine assembly in midair, walking through the piston strokes and timing alignments before they ever touch a physical tool. This solves the primary friction point for the US worker: the cost of entry into a high-paying trade. If you can learn in 6 months via high-fidelity simulation what used to take 4 years of apprenticeship, the economic potential for the individual and the industry changes overnight. To understand why this is happening now, we have to look at the sheer data density of a modern vehicle. In the year 2000, a typical car had perhaps 20 electronic control units. Today, a high-end truck or EV can have over 100. Traditional training methods rely on 2D diagrams, wiring schematics that look like a bowl of spaghetti printed on a flat piece of paper. The cognitive load required to translate a 2D drawing into a 3D physical object is one of the leading causes of diagnostic error. Historical trends in cognitive psychology suggest that spatial learning by doing in a 3D environment, leads to much higher retention rates. We are going to break down the specific hardware being deployed in American shops right now, from the Microsoft HoloLens 2 to the Apple Vision Pro, and how these devices are being used to X-ray vehicles in real time. We will examine how a technician in rural Nebraska can now put on a headset and have a world-class engineer from Detroit virtually teleport into the shop to guide them through a complex repair using 3D annotations that stay pinned to the physical car. This is the end of the guess and check era of mechanics. In this masterclass, we are going to dive into the technical architecture of these 3D systems. We will look at how CAD data, the original digital blueprints used to design the car, is being converted into gamified training modules. You will see how a technician can practice a high-risk battery de-energization procedure 1,000 times in a virtual environment where a mistake results in a game-over screen rather than a life-threatening electrical discharge. We will also discuss the career trajectory for those entering this field. We aren't just talking about fixing cars. We are talking about the emergence of the diagnostic data specialist. But there is a controversial side to this. As we move toward 3D-assisted repair, what happens to the soul of the mechanical trade? Does the feel for a machine disappear when it is mediated by a digital screen? We will analyze the data on mechanical empathy and whether 3D training produces better parts changers or better problem solvers. This video will provide the roadmap for anyone looking to understand the next decade of the automotive industry. Whether you are a car owner frustrated by repair costs, a student looking for a future-proof career, or a tech enthusiast curious about the practical applications of the metaverse, this is the definitive look at the 3D revolution. We are moving past the era where you need to be a grease monkey to survive in the shop. The future belongs to those who can navigate the digital and physical worlds simultaneously. By the end of this series, you will understand exactly how the vehicles on American roads are being transformed from inscrutable machines into interactive 3D environments, and how you can position yourself to benefit from this shift. We are starting with the why, the massive technical debt the auto industry has accumulated, and then we will move into the how, showing you the exact software and spatial interfaces that are currently being rolled out across the United States. The era of the 3D mechanic hasn't just arrived. It is currently rewriting the rules of the American road. Stay with us as we open the hood on the most significant technological leap in automotive history since the invention of the assembly line. We are about to see exactly what happens when the digital world finally catches up to the heavy metal of the auto shop. To understand why this transition is so violent and necessary, we have to look at the life of a technician named Jackson in Columbus, Ohio. It is March 2026, and Jackson has been a lead tech at a high-volume domestic dealership for 15 years. In 2022, when a new hybrid powertrain came into his bay with a cryptic thermal management error, Jackson would spend 3 hours scrolling through a service portal on a ruggedized laptop. He would cross-reference static 2D wiring diagrams with black and white photos that were often 5 years out of date. He would have to mentally map a flat line on a screen to a physical coolant hose tucked behind a steering rack. This mental translation is where the majority of diagnostic errors occur. Historical trends in automotive service show that misdiagnosis costs American dealerships billions of dollars annually in unnecessary parts replacement and lemon law buybacks. Now imagine Jackson in 2026. He walks up to a 2026 electric pickup truck. Instead of reaching for a scan tool first, he puts on a lightweight pair of industrial mixed reality glasses. As he looks at the front of the vehicle, the software identifies the VIN through optical recognition and pulls the specific digital twin for that exact build. Suddenly, Jackson sees a translucent, color-coded map of the high-voltage cooling circuit overlaid perfectly onto the physical truck. He can see where the pumps are located, which valves are currently open, and most importantly, he sees a pulsing red aura around a specific junction. The 3D system has processed the telematics data and is showing him exactly where the flow restriction is occurring. He isn't guessing. He is seeing data manifested in physical space. This is the fundamental shift from descriptive repair to prescriptive spatial guidance. The technology driving this is rooted in the convergence of CAD to AR pipelines. In the past, the computer-aided design files used by engineers to build the car were kept in a vault, far away from the technicians who had to fix them. Today, companies like Mercedes-Benz and Ford have streamlined the process of turning those massive engineering files into lightweight, interactive 3D assets for training. A case study from a major European manufacturer recently demonstrated that technicians using 3D spatial instructions were able to perform a complex battery-to-motor interconnect procedure correctly on their first attempt, whereas the group using traditional tablet-based instructions had a 40% failure rate. The potential outcomes of this are massive. We are looking at a future where the skill floor for entering the trade is lowered, but the ceiling for what a single technician can accomplish is raised through the roof. Let us break down the step-by-step process of a modern 3D training module. Step 1 is the calibration of the spatial environment. The trainee stands in a designated bay where the software maps the floor, the lift, and the vehicle's hard points. Step 2 is the interactive disassembly. Before a student like Sarah in Phoenix ever touches a real bolt, she performs the entire job in a full-scale virtual simulation. She uses haptic gloves that provide resistance when she handles a virtual impact wrench. If she tries to remove a high-voltage cable without following the lockout-tagout procedure, the simulation doesn't just give her a red X, it simulates the catastrophic failure, showing her in a slow-motion 3D render exactly how the arc flash would have occurred. This creates a physiological memory of the danger without the physical risk. Step 3 is the transition to the physical vehicle with an AR overlay. As Sarah moves to the real car, the 3D training system tracks her hand movements in real time. If she reaches for the wrong bolt, a virtual stop sign appears in her field of vision. If she needs to know the torque spec for a head bolt, she doesn't look away to a manual. The number is literally stuck to the bolt head in her vision. This eliminates the cognitive drift that happens when a human has to look away from a task to check instructions. By keeping the eyes on the work at all times, the training system encodes the mechanical process directly into the motor cortex. The depth of this training goes beyond just turning wrenches. We are now seeing the integration of 3D fluid dynamics and thermal modeling into training suites. Imagine if you could see the air moving through an intake manifold in real time. Imagine if you could see the friction points in a differential as they heat up during a simulated load test. In 2026, training platforms allow students to change variables, like oil viscosity or ambient temperature, and immediately see a 3D visualization of how those changes affect mechanical wear. This level of insight was previously reserved for PhD engineers with access to supercomputers. Now it is being delivered to 20-year-old apprentices in vocational schools across the United States. Data from the latest industry reports suggest that this spatial learning leads to a 60% increase in long-term knowledge retention. When you learn in 3D, your brain stores the information as a spatial memory, similar to how you remember the layout of your childhood home. When you learn from a 2D book, the brain stores it as semantic data, which is much easier to forget. This is why a technician trained in a 3D environment can often diagnose a vehicle they have never seen before. They understand the universal 3D logic of how components must interact within a physical envelope. Consider the economic implications for a small shop owner in rural America. Historically, sending a tech to a manufacturer training center meant paying for flights, hotels, and losing a week of labor. In 2026, that same training is delivered via a headset. The shop owner can buy a license for a 3D training module, and their tech can master the new model year on their lunch break. This democratization of high-level technical knowledge is the only thing standing between the independent repair industry and total obsolescence. If the small shops can't keep up with the 3D complexity of 2026 vehicles, the right to repair movement becomes a moot point because no one will have the tools or the training to actually execute the repairs. But this isn't just about making things easier. It is about a fundamental change in the definition of a mechanic. We are seeing the rise of the spatial data analyst. In the next part of this masterclass, we have to address the elephant in the room: the hardware. While the software sounds like a miracle, the physical devices required to run these 3D environments are currently in the middle of a brutal technological war. From the weight of the headsets to the battery life on the shop floor, the hardware limitations are the only thing holding back a total industry takeover. And more importantly, there is a hidden cost to this digital transition that no one is talking about. What happens when the manufacturer decides to turn off the 3D servers for a 10-year-old car? Does the vehicle become unfixable because the 3D instructions no longer exist? We are going to dive deep into the hardware bottleneck and the looming crisis of digital-only service data. If you think the shift to 3D is just a fancy way to see a bolt, you are missing the most dangerous part of this evolution. We need to talk about the proprietary lock-in that is being built into the very goggles Jackson is wearing. To understand the hardware bottleneck, we have to look at the physical reality of Jackson's workspace in Columbus. It is a Tuesday afternoon in July 2026, and the temperature inside the bay has climbed to 95 degrees with 80% humidity. Jackson is wearing an industrial-grade spatial computer, but this isn't the sleek, fragile consumer device you see in coffee shops. This is a ruggedized unit with an IP66 rating for dust and water resistance, featuring a reinforced titanium frame and a hot-swappable battery pack mounted to the back of the head strap to maintain perfect weight distribution. Historical trends in wearable technology have shown that if a device is uncomfortable or causes neck strain after 2 hours, technicians will simply stop using it. The potential outcomes of poorly designed hardware are a complete rejection of 3D training by the very workforce it is meant to save. The first major hardware hurdle is the field of view or FOV. In earlier iterations of augmented reality, the digital overlays were confined to a small box in the center of the user's vision. Imagine trying to look at a full-scale 3D engine schematic through a mail slot. By 2026, high-end industrial headsets have pushed the horizontal FOV to 120 degrees, allowing Jackson to see the entire drivetrain of a vehicle illuminated with data, without having to constantly whip his head back and forth. However, the cost of these units is staggering. A fleet of 10 headsets, complete with charging stations and localized edge computing servers to handle the rendering, can easily cost a shop owner $50,000. This is the new barrier to entry. In the 20th century, a mechanic bought a set of high-quality wrenches and was set for a career. In 2026, the tools have a shelf life of 3 to 5 years before the processors are too slow to run the latest 3D physics engines. Now, let us look at the concept of the proprietary lock-in, which is the most significant threat to the independent repair market since the invention of the computerized engine controller. Imagine Marcus, who owns a small 3-bay independent shop in Atlanta. Marcus has spent his life building a reputation for being able to fix anything that rolls through his door. But in 2026, a 2025 luxury SUV arrives with a suspension fault. Marcus puts on his headset, but instead of a 3D map of the air suspension system, he sees a digital padlock. To access the spatial data required to calibrate the sensors, Marcus has to pay a per-use fee to the manufacturer, or maintain a monthly gold-tier subscription that costs more than his shop's electricity bill. This is the walled garden of 3D auto repair. Manufacturers have realized that while they cannot legally prevent Marcus from turning a wrench, they can effectively block him by withholding the 3D assets. The service manual is no longer a book Marcus can buy. It is a stream of data that he must subscribe to. Without the 3D digital twin, the vehicle is an impenetrable black box. Historical trends in the software industry suggest that this service as a subscription model will only intensify. Case studies from the early 2020s involving tractor manufacturers and restricted diagnostic software served as the blueprint for this. By 2026, this has evolved into spatial data rights management. If you don't have the license, the 3D overlays simply don't render. You are left staring at a physical engine bay, while the digital blueprints are hidden behind a paywall. The step-by-step reality of this lock-in begins with the digital handshake. When Jackson or Marcus connects their headset to the vehicle's diagnostic port, the car sends a cryptographic token to the manufacturer's cloud server. The server verifies the technician's credentials, their insurance certification, and their subscription status. Only then does the high-fidelity 3D model begin to stream to the headset. If the shop's internet connection flickers, the 3D model stutters or disappears. This creates a massive dependency on high-speed infrastructure. In many rural parts of the United States, the lack of 6G or robust fiber optic networks is literally preventing mechanics from accessing the 3D training they need to fix modern cars. Furthermore, we must address the sensory gap. While 3D visuals are revolutionary, a huge part of being a master mechanic is the haptic feedback, the feel of a bolt reaching its yield point, or the vibration of a failing bearing. To bridge this, 2026 training suites are incorporating haptic gloves. These gloves use a network of micro-actuators and tendons to simulate the resistance of a physical object. Imagine if you are a student in a vocational school in Detroit. You reach out to grab a virtual 3D alternator. The gloves tighten around your fingers, simulating the weight and texture of the metal. If you cross-thread a virtual bolt, the glove provides a specific jarring resistance that teaches your muscles what a mistake feels like. But here is where the depth of the masterclass really begins to reveal the hidden risks. What happens to the secondary market? Potential outcomes for the used car industry are grim if 3D data is not preserved. Imagine it is the year 2035, and you are trying to restore a 2026 classic electric vehicle. If the manufacturer has gone out of business or simply decided to stop supporting the 3D data servers for that model, how do you fix it? The 2D schematics might not even exist anymore, as the car was designed, built, and serviced entirely in a 3D native ecosystem. This is the looming crisis of digital obsolescence. We are building a world where the ability to repair a machine is tied to a server that might not be there in 20 years. To counter this, a grassroots movement of 3D data archivists has emerged in 2026. These are independent developers who are using LiDAR-equipped drones and handheld scanners to pirate the 3D geometry of modern vehicles, creating open-source digital twins that cannot be locked away by manufacturers. This is the front line of the new right to repair war. It is no longer about the right to buy parts. It is about the right to access the 3D coordinates of those parts. As Jackson works on that luxury SUV in Columbus, he is currently participating in this ecosystem. Every time he uses his headset, the manufacturer is collecting data on how he moves, which components he touches first, and how long it takes him to complete a task. This data is fed back into an AI that optimizes the 3D training for the next generation of techs. Jackson isn't just a mechanic anymore. He is a data point in a massive, closed-loop machine learning system. This brings us to the most unsettling question of all. If the 3D training system becomes good enough, does the technician even need to understand how the car works? If the goggles are telling you exactly where to move your hand and which direction to turn the wrench, are you a master of your craft? Or are you just a human actuator for an AI-driven repair platform? The line between human skill and machine guidance is blurring. In the next part of this deep dive, we are going to look at the rise of real-time expert assistance. We will see how a technician with 6 weeks of training can perform a task that used to require 20 years of experience, and the terrifying implications this has for wages and job security in the American automotive sector. We have to talk about the ghost in the machine, the remote master techs who are now riding shotgun in the headsets of thousands of apprentices simultaneously. If you think your job is safe because it requires physical labor, you need to see how remote spatial presence is about to change everything. To understand the sheer power of remote spatial presence, we need to look at a junior technician named Leo in Seattle. It is June 2026, and Leo has only been on the job for 6 months. In the traditional era of automotive repair, Leo would be restricted to changing oil, rotating tires, and perhaps performing basic brake jobs under the watchful eye of a senior lead. He would be years away from touching a complex powertrain. But today, Leo is standing in front of a 2026 hydrogen-electric heavy-duty truck with a catastrophic failure in its fuel cell management system. This is a machine so complex and so dangerous that only a handful of certified master technicians in the entire country are truly qualified to open the casing. Historically, this truck would have to be towed hundreds of miles to a specialized hub, costing the logistics company thousands of dollars in downtime and transport. Instead, Leo puts on his spatial computing headset and initiates a remote expert session. Within seconds, a master technician named Elena, who is currently sitting in a dedicated support center in Dearborn, Michigan, enters Leo's field of vision. But Elena isn't just a face on a screen. Through the power of spatial anchors and real-time LiDAR mapping, Elena's digital avatar appears to be standing right next to Leo in the Seattle Bay. She sees exactly what he sees through the high-definition cameras on his headset, but with one critical addition. She can reach into his physical world with virtual hands. Elena instructs Leo to begin the high-voltage isolation procedure. As she speaks, she uses her stylus in Michigan to draw a glowing green circle around a specific locking pin in Leo's physical environment. Leo doesn't have to look at a manual to find the pin. It is literally highlighted in his reality. When he reaches for the pin, Elena sees his hand movements with millisecond latency. She stops him. She points out a microscopic hairline crack in the connector housing that Leo had missed, a detail captured by the headset's macro-focus lenses and transmitted to her 8K monitor halfway across the country. This is the ghost in the machine. Leo is providing the physical labor, the tactile dexterity, and the on-site presence, while Elena provides the decades of diagnostic intuition and high-level certification. The technical architecture making this possible in 2026 relies on a concept known as spatial synchronization. The headset in Seattle is constantly generating a point cloud map of the engine bay. This map is streamed via a high-bandwidth 6G connection to the expert's terminal. The expert's movements are then mapped back onto that point cloud. If Elena points to a bolt, the coordinate is translated from her virtual space to Leo's physical space with sub-millimeter accuracy. Historical trends in remote assistance initially struggled with parallax error, where the expert thought they were pointing at one thing but the technician saw them pointing at something else. By 2026, advanced eye tracking and depth sensing cameras have virtually eliminated this discrepancy. This leads us to a profound and somewhat uncomfortable shift in the American labor market: the rise of the human actuator. In this model, the on-site technician is effectively a set of remote-controlled hands for a centralized brain. Case studies from the aerospace industry, which pioneered this tech, suggest that a novice technician guided by a remote expert can perform complex tasks with a 98% accuracy rate on their first attempt. The potential outcomes for the automotive industry are twofold. On one hand, it solves the massive technician shortage by allowing a single master tech to oversee 20 different repairs in 20 different states simultaneously. Elena in Michigan can jump from Leo's fuel cell repair in Seattle to a complex transmission diagnostic in Florida with a single click. On the other hand, what does this do to the wages and career trajectory of someone like Leo? If the intelligence of the repair is hosted in the cloud, does Leo ever actually learn the craft? Imagine if Leo's headset loses its connection. If he has spent his entire 6-month career merely following the glowing lines and verbal cues of a remote master, he has not developed the internal mental models required for independent problem solving. He is a master of following instructions, but not a master of the machine. This creates a dependency loop. Historical trends in automation show that when you simplify a task through technology, the economic value of the person performing that task often decreases. We are facing a future where the local mechanic might be paid more like a delivery driver than a specialized engineer, because the engineering is being done by a subscription-based AI or a remote expert center. Step by step, let's look at how this remote session transforms a 3-day repair into a 3-hour one. Step 1. The pre-diagnostic. The vehicle's onboard AI identifies a fault and automatically pushes the relevant 3D service data to the shop's local server before the truck even arrives. Step 2. The spatial handshake. Leo connects his headset to the vehicle, and the remote expert is summoned based on the specific fault code. Step 3. Guided intervention. The expert uses spatial annotations to guide Leo through the disassembly. Step 4. Verification. The expert takes a high-resolution 3D scan of the completed repair to verify that every bolt is torqued and every seal is seated. Step 5. The digital log. The entire session is recorded and indexed, creating a 3D video manual that other technicians can use as a reference later. However, the depth of this masterclass requires us to look at the edge cases. Imagine a scenario where a technician is working on a high-risk system, such as a compressed natural gas tank. In 2026, safety protocols in these 3D systems are absolute. If the remote expert sees the technician move toward a high-pressure valve without the correct protective equipment, the expert can literally freeze the technician's screen, replacing their vision with a massive red warning until they step back. The system can even interface with the shop's smart tools. If Leo tries to use a standard wrench on a bolt that requires a non-conductive tool, his headset will recognize the tool in his hand via computer vision and prevent the next step of the instruction from appearing. The potential outcomes for insurance companies are significant. By 2026, many commercial insurance providers are beginning to offer lower premiums to shops that use certified 3D remote assistance. The logic is simple. A recorded expert-guided repair has a much lower probability of a comeback or a secondary failure. This data-backed certainty is the holy grail of the repair industry. It removes the human element of, "I think I tightened that," and replaces it with a time-stamped 3D verified record of the work. But there is a darker side to the ghost in the machine. We have to discuss the concept of surveillance training. Because the headset is recording everything Leo does, the manufacturer is not just helping him fix the car. They are timing him. They are measuring his hand speed, his tool selection efficiency, and even his heart rate via sensors in the head strap. This data is used to set labor times that are physically impossible for a human to meet without total reliance on the 3D system. This is the Taylorism of the 21st century. The machine is no longer just a tool. It is a supervisor. This brings us to a terrifying realization. If a human expert can guide Leo in real time, how long will it be before that expert is replaced by a large action model? An AI that has watched 1,000,000 hours of these 3D repair sessions and can now project its own virtual hands into Leo's vision? We are approaching the point where the master technician isn't a person at all, but a set of algorithms running on a server in Nevada. In the next part of this series, we are going to dive into the rise of the AI mentor. We will see how 3D repair is moving from human-to-human assistance to machine-to-human guidance, and why your next mechanic might be taking orders from an entity that doesn't have a pulse. If you thought being a human actuator for a person in Michigan was a shift, wait until you see what happens when the AI takes the lead. The training wheels are about to become the driver. The transition from human-to-human remote assistance to pure machine-to-human guidance is the single most disruptive event in the history of the American trade school. In 2026, we are no longer just talking about a person in Michigan helping a person in Seattle. We are talking about the emergence of the Autonomous Diagnostic Mentor, or ADM. To see this in action, we have to travel to a vocational tech center in Austin, Texas, where a 19-year-old student named Chloe is standing before a powertrain she has never seen in person. This is a 2027 pre-production model, utilizing a modular solid-state battery architecture. In the old world, Chloe would be forbidden from touching this. The liability alone would be a nightmare. But Chloe is wearing a Series 4 Vision Suite, and she isn't waiting for a call from an expert. She is being guided by a large action model that has ingested every engineering schematic, every assembly line video, and every crash test report associated with this vehicle. The AI Mentor does not just provide a voice in Chloe's ear, it provides a comprehensive 3D ecosystem. As she approaches the vehicle, the AI performs a real-time semantic segmentation of the entire bay. It identifies the specific serial numbers on her torque wrenches, the state of the hydraulic lift, and even the ambient light levels. Imagine if every tool in your hand was suddenly aware of the task at hand. When Chloe picks up a digital multimeter, the AI highlights the exact 2 pins on a high-voltage connector she needs to probe. But it goes deeper. The AI uses predictive gaze tracking. It notices that Chloe's eyes are darting toward a cooling line that shouldn't be pressurized, but is. Before she even moves her hand, a translucent 3D warning shield manifests in her vision, blocking the dangerous path and showing her a simulated video of what would happen if she disconnected that line prematurely. This is the era of the phantom mechanic. As Chloe works, a life-sized, translucent 3D avatar of a master technician, generated by the AI, performs the task alongside her. This avatar shows her the exact body mechanics required. It demonstrates how to brace her shoulder when removing a heavy shielding plate to prevent a strain injury. It shows the precise flick of the wrist needed to seat a delicate fiber optic sensor. Chloe isn't reading a manual. She is mimicking a perfect digital ghost. Historical trends in motor skill acquisition indicate that this type of observational learning, when combined with immediate haptic feedback, can reduce the time required to master a physical craft by over 80%. We are seeing potential outcomes where a high school graduate can reach the technical proficiency of a 10-year veteran in less than 12 months of intensive 3D simulated and AI-guided training. But let us look at the data driving this. In 2026, the computing power required to run these spatial AI models has shifted from massive server farms to edge computing nodes located right inside the dealership. These models are trained on what is known as synthetic repair data. Because there aren't enough real-world videos of every possible repair for every new car, manufacturers use high-fidelity physics engines to simulate millions of failed repairs. They simulate bolts snapping, seals leaking, and wires shorting out. The AI learns from these millions of virtual failures, so when Chloe encounters a unique 1-in-a-million edge case, the AI has already seen a version of it in a simulation. This is why the AI Mentor is, in many ways, more capable than a human expert. A human expert has the experience of 1 lifetime. The AI Mentor has the experience of 10,000 simulated lifetimes. The step-by-step integration of this AI into the American workforce is happening in 3 distinct phases. Step 1 is the passive overlay. In this phase, the AI simply labels parts and provides torque specs as the technician works. Step 2 is the active intervention. This is where the AI begins to monitor the technician's performance in real time, correcting their technique and preventing errors before they happen. Step 3, which is where we are in 2026, is the generative guidance phase. Here, the AI isn't just following a pre-written script. If Chloe encounters a stripped bolt or a modified aftermarket part that isn't in the original blueprints, the AI uses its computer vision to analyze the anomaly and generates a custom, 3D printable tool design or a modified extraction procedure on the fly. It is a real-time engineering partner. However, we must address the black box liability crisis. Imagine if the AI Mentor provides Chloe with a 3D instruction that leads to a catastrophic battery fire. In 2026, the legal frameworks in the United States are still catching up to this. Who is responsible? Is it Chloe, who followed the instruction? Is it the shop owner, Marcus, who provided the headset? Or is it the software developer who trained the AI? Case studies from the early autonomous driving lawsuits are being used as a template, but the complexity of a manual repair adds a new layer of ambiguity. This is why many 3D training platforms now require a digital notary. Every step Chloe takes is recorded in a tamper-proof 3D log. If a repair fails, investigators can play back the entire session in a 3D reconstruction to see exactly where the deviation occurred. whether it was a software glitch or a human error. There is also the psychological impact of working under the constant, unblinking eye of a machine. In our Austin case study, Chloe reports that while she feels safer, she also feels a strange sense of automation bias. She finds herself trusting the 3D overlays even when her gut instinct tells her something is wrong. This is the danger of the perfect mentor. When the technology is this good, the human brain tends to offload its critical thinking. Historical trends in aviation show that when pilots rely too much on flight directors, their basic stick and rudder skills can atrophy. In the automotive world, we are seeing the emergence of visual dependency. Some young technicians struggle to even identify a basic alternator if they aren't wearing their glasses. They have lost the ability to read a machine without digital labels. Furthermore, we need to consider the impact on the old guard. In shops across America, there is a growing divide between the analog techs and the digital actuators. The older generation, who spent decades developing a feel for internal combustion, often find the AI mentor intrusive. They argue that the AI can't hear the subtle skip in a timing chain or feel the microscopic play in a wheel bearing. But the data from 2026 suggests otherwise. Modern headsets are equipped with high-sensitivity acoustic sensors that can perform a Fourier transform on engine noise, identifying a bearing failure months before a human ear could detect it. The AI isn't just replacing human sight, it is augmenting every human sense. The economic potential for this is staggering. By removing the need for expensive, centralized training facilities, we are seeing a revival of the home mechanic. In 2026, a high-end 3D training subscription allows a hobbyist in their own garage to perform professional-grade repairs on complex EVs. This is the ultimate democratization of the trade, but it also threatens the business model of the traditional dealership. If a DIYer with an AI mentor can do the work of a certified tech, why would they ever pay $200 an hour for labor? We are standing at a crossroads where the craft of the mechanic is being digitized and commodified. The AI mentor is the final bridge between the human hand and the machine's soul. But as we move deeper into this decade, a new and even more radical technology is beginning to surface in the elite research labs of Detroit and Silicon Valley. It's a technology that doesn't just show you how to fix the car. It allows the car to fix itself using the very 3D data we've been discussing. We need to talk about self-healing architectures and robotic swarm maintenance. If the AI can guide Chloe, how long until it simply guides a robotic arm? The 3D training you are seeing today is actually the final stage of human involvement in automotive repair. In the next part, we are going to explore the rise of the automated bay, a world where the human mechanic isn't just being guided by an AI, but is being phased out entirely by the very 3D systems they help train. If you think the ghost in the machine was haunting, wait until you see the empty shop. To understand the empty shop, we have to travel to a high-density urban transit hub in San Jose, California. It is September 2026, and a man named David is the sole occupant of a facility that services 500 autonomous electric shuttles. In 2020, a fleet of this size would have required a staff of 50 technicians, a massive inventory of physical parts, and millions of dollars in overhead for manual labor. But David is not a mechanic in any traditional sense. He doesn't own a single wrench. He sits in a glass-walled observation deck overlooking a series of white, surgical-grade bays. When a shuttle pulls in, it isn't greeted by a person. It is met by a multi-axis robotic gantry system that has already downloaded the vehicle's entire 3D health history via a 6G telemetry burst 3 miles before the vehicle arrived at the gate. This is the manifestation of the automated bay. The process begins with what is known as a total vehicle scan. As the shuttle rolls over a glass floor, a series of high-speed LiDAR and ultrasonic sensors create a real-time 3D reconstruction of the chassis, looking for stress fractures, road debris, or thermal anomalies that the onboard sensors might have missed. Simultaneously, a drone-mounted camera array performs a 360-degree external inspection, using computer vision to identify a single loose rivet or a hairline crack in a sensor housing. All of this data is compared against the digital twin of the vehicle stored in the cloud. Historical trends in industrial automation show that machines are infinitely better at spotting these minute deviations than human eyes, which are prone to fatigue and distraction. Once the 3D scan is complete, the repair phase begins. Imagine a robotic arm equipped with a tool-changing head. Because the entire vehicle has been mapped in 3 dimensions down to the micron, the robot doesn't need to hunt for a bolt. It knows exactly where it is in 3D space. If a cooling fan needs replacement, the robotic gantry selects the precise socket, moves at speeds a human could never safely achieve, and executes the swap with perfect torque every single time. There is no trial and error. There is no rounded-off bolt head. There is no forgotten gasket. This is the potential outcome of a 3D native design. When cars are built by robots using 3D data, they are designed to be fixed by robots using that same data. Let us look at a specific case study from a 2026 logistics company operating in the American Midwest. They implemented an automated tire and brake suite. Traditionally, checking brake pad thickness and tire tread depth was a manual, tedious process. Now, as the trucks roll through a 3D scanning portal, a laser triangulation system measures the tread depth at 30 different points across the tire width. If the data shows an uneven wear pattern, the 3D system doesn't just flag it for replacement. It calculates the exact suspension misalignment causing the wear. The truck is then automatically routed to a robotic alignment rack where actuators adjust the tie rods, while the truck is still moving slowly through the bay. The entire diagnostic and adjustment cycle takes less than 90 seconds. No human was involved. No human was even notified until the job was already done, and the bill was generated. This leads us to the concept of self-healing architectures. In the vehicles of 2026, the 3D data isn't just used for external repair, it is used for internal rerouting. Imagine a scenario where a 2026 SUV detects a localized short circuit in its secondary wiring harness. In the past, this would cause a blown fuse and a dead vehicle. Today, the vehicle's central nervous system uses its internal 3D map to identify redundant pathways. It can physically switch the power load to an alternate circuit or, in some cases, use liquid polymer injectors built into high vulnerability areas to seal, a leak or insulate a damaged wire. This is not science fiction. It is the logical extension of the 3D mapped vehicle. The car becomes an active participant in its own survival. But what about the more complex, messy repairs that robots usually struggle with? This is where robotic swarm maintenance enters the picture. Instead of one large robot, 2026 labs are testing swarms of micromanipulators. Imagine if, instead of removing an entire engine to fix an internal sensor, a series of snake-like robots, no thicker than a human finger, could enter through the intake manifold. Guided by the 3D digital twin, these micro-robots navigate the internal geometry of the engine, using 3D printed tips to solder a connection or clear a blockage. They are essentially surgeons for machines. This level of precision is only possible because we have perfect 3D maps of every internal cavity of the vehicle. The economic reality for David in San Jose is that his role has shifted from doer to orchestrator. He monitors the system health of the entire shop. When the 3D system encounters an anomaly, a piece of road debris that is wedged in a way the robot doesn't recognize, David doesn't go down with a pair of pliers. He puts on a VR headset and takes remote control of the robotic arm, using the 3D data to feel his way through the problem from his desk. He is a fleet orchestrator, managing the efficiency of an entire ecosystem. Data from 2026 labor reports suggests that while the number of traditional mechanic jobs is shrinking, the demand for these high-level automation supervisors is skyrocketing, with salaries reflecting the massive increase in productivity they represent. Step by step, the transition to the empty shop looks like this. Step 1. The shift to 3D native vehicle design, where every part is a unique digital asset. Step 2. The deployment of 3D scanning infrastructure at every major transit point. Step 3. The integration of robotic actuators into the shop environment. Step 4. The removal of the human from the routine maintenance loop. By 2026, we are firmly in Step 4 for commercial fleets. The potential outcomes for the average American consumer are a radical reduction in vehicle downtime. Your car doesn't go to the shop for a week. It goes to a 3D portal for 6 minutes. However, there is a massive open loop in this transition. If the shop is empty and the car is fixing itself and the robots are doing the labor, who owns the data? In this 3D automated world, the one who owns the 3D digital twin owns the vehicle forever. We are moving into an era of hard-coded obsolescence. If the manufacturer decides a 3D printed part is no longer authorized, the robotic bay will simply refuse to install it. The machine will not disobey its code. This brings us to a critical junction in our masterclass. We have seen how 3D training creates a better mechanic, and how 3D data creates an automated shop. But now we have to look at the dark side of this 3D revolution: the end of ownership. In the next part, we are going to explore the digital lockdown, We will look at how 3D auto repair is being used to enforce a subscription-based world where you never truly own your car, you only license its functionality. We will see how 3D watermarking and encrypted parts are turning the dream of the self-fixing car into a nightmare of corporate control. If the robots are the only ones who can fix the car, and the robots only listen to the manufacturer, what happens to you when your subscription expires in the middle of a highway? We are going beyond the training and into the terrifying legal reality of the 3D integrated vehicle. You need to see how the empty shop is actually a cage for the American driver. To understand the mechanics of the digital lockdown, we must look at a consumer named Ethan in Chicago. It is November 2026, and Ethan has just purchased a certified pre-owned 2025 hybrid sedan. He is a savvy car owner who believes in the traditional American ideal of ownership. The idea that once you pay for a machine, you have the right to modify, maintain, and understand every bolt of that machine. But Ethan is about to discover that in the age of 3D integrated repair, the physical car is merely a shell, while the true vehicle exists as an encrypted data stream on a corporate server. Imagine Ethan notices a slight vibration in his steering rack. In 1996, he would have crawled under the car with a flashlight. In 2026, he drives into a local automated diagnostic kiosk. The high-speed 3D scanners immediately identify the issue: a worn bushing in the electric power steering assembly. The system generates a 3D model of the fault and displays it on Ethan's phone. It looks like the future of convenience. But then the screen flashes a warning. The 3D geometry for this specific steering rack is protected by Level 5 geometric encryption. To unlock the 3D repair instructions for his own car, Ethan must pay a $29 spatial access fee. If he wants to use an aftermarket bushing, one that is mechanically identical but costs half the price, the system informs him that the car's 3D native controller will not recognize the new part's spatial signature, potentially disabling the steering assist for safety reasons. This is the birth of Geometric Digital Rights Management, or GRDM. Historical trends in the software and gaming industries have now fully migrated to the automotive shop. We are seeing a shift where the physical dimensions of a part are treated as protected intellectual property. In 2026, manufacturers are using 3D watermarking on their components. This isn't a serial number etched into the metal. It is a microscopic, mathematically precise variation in the part's surface geometry that can only be seen by high-fidelity 3D scanners. If Ethan's car detects a part that doesn't have this geometric handshake, the software-defined vehicle can put itself into a limp mode, restricting speed to 20 miles per hour until a verified 3D part is installed. Let us look at a case study from a major domestic manufacturer that recently implemented the secure spatial architecture. They argued that this was necessary for safety, ensuring that only parts with the correct structural integrity were used in high-stakes repairs. However, the potential outcomes for the American consumer are a total loss of mechanical agency. Case studies from the early 2020s involving printer ink and tractor software were just the beginning. By 2026, this has evolved into what legal experts call the end of the second-hand market. If you cannot fix a car without a 3D data key that the manufacturer refuses to sell to anyone but their own dealers, then the car has no value once it leaves the warranty period. It becomes a disposable appliance, regardless of how well the metal and rubber have been maintained. The step-by-step reality of this lockdown is cold and efficient. Step 1. The vehicle's central nervous system continuously monitors the 3D mesh of its components. Step 2. Any physical change, even a bolt being tightened by an unauthorized 3D headset, is logged as a spatial deviation. Step 3. The manufacturer sends an over-the-air notification that the vehicle's structural integrity certificate has been revoked. Step 4. Insurance providers, who are now directly linked to this 3D data stream, automatically increase Ethan's premiums or cancel his coverage because the vehicle is no longer 3D verified. But the depth of this crisis goes even further. We need to talk about software-gated hardware. Imagine Ethan's car has a perfectly functional motor for its adjustable seats. One day, the 3D system updates and the seats stop moving. Ethan receives a message: your Comfort Tier subscription has expired. To re-enable 3D spatial control of your seating position, please renew for $15 a month. The hardware is there. Ethan has already paid for the motor and the leather and the wiring. But the 3D instruction that tells the motor where to stop and start is now a leased service. Historical trends suggest that by 2030, nearly 40% of a vehicle's mechanical functions could be behind these digital paywalls. The impact on the American worker is equally devastating. Small shop owners like Marcus in Atlanta are being squeezed out of the market. Even if Marcus has the 3D headsets and the robotic bays, he cannot compete if he is forced to pay license royalties on every bolt he turns. This creates a consolidation of repair. Only the largest, most capitalized dealership groups can afford the 3D data tiers required to service modern fleets. The local mom-and-pop shop is being regulated out of existence, not by the government, but by the 3D data protocols of the manufacturers. Furthermore, we must address the digital ghosting of older models. Imagine it is 2026 and you are driving a 2018 model that was one of the first to use 3D integrated diagnostics. The manufacturer has just released their 2027 lineup and decided that the servers hosting the 3D assets for the 2018 models are no longer economically viable to maintain. Overnight, your car becomes unfixable. No mechanic, no matter how skilled, can access the 3D maps required to calibrate your sensors. This is hard-coded obsolescence. Your car is perfectly fine, but its digital twin has been deleted. This creates a terrifying legal reality. In the United States, the right to repair movement is currently fighting a multi-front war against these 3D lockdowns. But the manufacturers are using the Digital Millennium Copyright Act, or DMCA, to argue that the 3D geometry of a car is copyrighted code. According to this logic, when Ethan tries to use a 3D scanner to figure out how to fix his own steering rack, he isn't just a mechanic. He is a hacker committing copyright infringement. The cage for the American driver is built out of 3D data points and legal loopholes. But where there is a lockdown, there is always a rebellion. In the shadowy corners of the internet and in secret garages across the Midwest, a new breed of digital grease monkeys is emerging. These are the people who are finding ways to jailbreak the 3D architecture of modern cars. They are using open-source LiDAR and 3D printing their own unlocked sensors. This is the new underground economy of the 2020s. As Ethan sits in his car in Chicago, frustrated by the spatial access fee on his screen, he sees a sticker on the kiosk wall with a QR code. It says, "Own your car again. Join the mesh." This is the opening of a new loop. We have seen how 3D training changed the mechanic, how automation changed the shop, and how DRM changed ownership. Now we have to look at the counter-revolution. In the next part, we are going to dive into the Great Jailbreak. We will see how independent engineers are cracking the 3D watermarks and creating a shadow market of open-source 3D repair data. If the manufacturers thought they could lock the American driver out of their own engine, they severely underestimated the ingenuity of a person with a 3D scanner and nothing left to lose. We are going into the world of dark repairs and the high-stakes game of cat and mouse between corporate servers and independent garages. The 3D war is just getting started. In a dusty industrial park on the outskirts of Omaha, Nebraska, a technician named Riley is currently staring at a 2024 electric delivery van that has been bricked by a software update. It is July 2026, and the company that manufactured this van filed for Chapter 11 bankruptcy 3 months ago. Their central servers, which hosted the proprietary 3D diagnostic maps and the cryptographic keys required to bleed the regenerative braking system, have been taken offline by a liquidator. To the traditional eye, the van is in perfect mechanical condition. But because its 3D digital twin is locked behind a dead server, the vehicle is legally and technically a 3-ton paperweight. This is the catalyst for the Great Jailbreak of 2026. Riley represents a growing movement of independent engineers who are refusing to let the 3D revolution turn the American car into a disposable piece of consumer electronics. Imagine if your house became uninhabitable because the company that built the front door lock went out of business and took the digital key with them. That is the reality for thousands of fleet owners today. To solve this, Riley is using a technique known as spatial reverse engineering. He isn't using the manufacturer's $5,000 authorized headset. Instead, he is wearing a custom-built rig running an open-source Linux kernel designed for spatial bypass. The first step in Riley's process is what the underground calls geometric ripping. Since he doesn't have the official 3D CAD files, he has to recreate them from scratch. He uses a handheld industrial-grade LiDAR scanner that fires millions of laser pulses per second to create a high-density point cloud of the van's internal components. Historically, this would have taken weeks of professional surveying. In 2026, Riley can walk around the engine bay for 10 minutes and generate a 3D mesh with sub-millimeter accuracy. This is the foundation of the mesh, a decentralized peer-to-peer repository where technicians across the United States are uploading cracked 3D models of proprietary parts. Once Riley has the 3D mesh, he has to deal with the 3D watermark. As we discussed in the previous part, modern parts have microscopic geometric variations that act as a digital handshake. Riley's software analyzes the 3D scan and identifies the signature of the watermark. He then uses a generative AI tool to create a geometric patch. This patch is essentially a piece of code that tricks the vehicle's central computer into thinking it is seeing a verified, factory-authorized component. Potential outcomes of this approach include a thriving secondary market for refurbished 3D parts, but it also carries significant risks. Historical trends in the cybersecurity world show that whenever a system is jailbroken, the manufacturer responds with more aggressive kill switches. Let us look at a case study from a shipping conglomerate in Detroit. In early 2026, they faced a projected loss of $4 million because their fleet of aging hybrid trucks required a mandatory 3D sensor calibration that was only available through a high-priced subscription they could no longer afford. They hired a team of dark repair specialists, technicians like Riley who operate in the legal gray area of the right to repair movement. These specialists deployed a localized man-in-the-middle spatial attack. They intercepted the 3D data stream between the vehicle's sensors and the onboard computer, replacing the encrypted factory data with an open-source 3D map. The trucks were back on the road in 48 hours at a fraction of the cost. However, the depth of this conflict involves the physical hardware of the repair itself. In 2026, many manufacturers have moved to integrated assemblies, where a single failed $3 bearing is encased in a 3D printed titanium housing that cannot be opened without specialized sonic cutters. Riley's response to this is 3D printed tooling. Using the 3D data from the mesh, he can print a custom extraction tool in under 4 hours that is perfectly keyed to the unique geometry of that specific assembly. This is a level of precision that was previously impossible for a small shop. We are seeing a shift from the universal wrench to the single-use digital tool. The step-by-step logic of a dark repair session looks like this. Step 1. The technician bypasses the headset's geographic lock using a decentralized VPN, making the manufacturer's server think the repair is happening in a region with more lenient repair laws, like the European Union. Step 2. The technician uses an unfiltered 3D overlay that displays hidden diagnostic codes the manufacturer usually hides from independent shops. Step 3. The technician performs the mechanical work, guided by community-verified 3D instructions that are often more detailed than the factory manuals because they include real-world fixes for common design flaws. Step 4. The technician uses a certificate emulator to sign off on the repair in the vehicle's digital log, preventing the car from flagging an unauthorized service event. This brings us to the concept of the open-source digital twin. In 2026, groups like the Automotive Freedom Foundation are working to create a complete, unencrypted 3D map of the most popular vehicles on American roads. Imagine a world where, instead of paying for a subscription, you download the Linux of cars. You put on your 3D glasses, and you see a repair interface built by the community for the community. There are no paywalls, no spatial access fees, and no data harvesting. The potential outcomes for the American consumer are a return to the era of the 100-year car, vehicles that can be kept running indefinitely because the knowledge to fix them is held in a public commons rather than a corporate vault. But the risks are real. When you use a community-generated 3D map to calibrate a steering sensor or a brake actuator, you are trusting the math of a stranger on the internet. Case studies of early 3D printed medical devices showed that even a 1% deviation in geometry can lead to catastrophic failure under stress. In the automotive world, a miscalibrated 3D sensor could mean the difference between a successful emergency stop and a collision. This is why the 3D war is not just about money, it is about the verification of truth. Who do you trust to tell you the 3D coordinates of your own car? The manufacturers argue that by jailbreaking these systems, technicians are creating unpredictable machines that are a menace to public safety. They are lobbying for federal laws that would make the possession of unfiltered 3D diagnostic software a felony. Meanwhile, the independent shops argue that the manufacturers are using safety as a smokescreen for monopoly. This is the high-stakes game of cat and mouse currently playing out in garages from Seattle to Miami. Riley in his Nebraska shop is at the front line. Every time he successfully bypasses a 3D lock, he is contributing a tiny piece of data to the mesh, making the next repair easier for someone else. As the sun sets over the industrial park, Riley finishes the geometric patch on the delivery van. The dashboard, which had been glowing with red error messages for weeks, suddenly turns a calm, steady green. The van is alive again, disconnected from its dead corporate parents and now part of the decentralized mesh. But Riley knows this victory is temporary. The manufacturer's next update will likely include spatial heartbeat checks, a system that verifies the 3D geometry of the car every 30 seconds while driving. The 3D war is entering its most dangerous phase. We have seen how training changed, how shops became automated, and how owners were locked out. Now we are seeing the rise of the ghost shops and the underground 3D economy. But there is one final piece of this puzzle that we haven't touched yet. What happens when the AI that designs the cars realizes that humans are jailbreaking the 3D data? We are moving toward the self-obfuscating machine, vehicles that are designed by AI to be fundamentally incomprehensible to the human brain, even with 3D assistance. In the next part, we are going to look at the rise of the inscrutable engine. We will explore how AI is being used to design mechanical systems so complex that no 3D map can simplify them for a human technician. We are approaching the repairability singularity, where the gap between machine intelligence and human understanding becomes a permanent chasm. If you thought the jailbreak was the end of the story, you aren't ready for what the AI is building next. In a laboratory cleanroom in Detroit, Michigan, it is March 2026, and a senior forensic engineer named Sam is staring at a component that defies 30 years of his mechanical intuition. This is the Central Thermal Management Unit for a 2027 prototype electric flagship. In the year 2020, such a part would have consisted of a series of recognizable pipes, a water pump, and perhaps a thermostat housing, discrete components that Sam could identify, test, and replace. But the object on Sam's bench looks less like a car part and more like a bleached piece of deep-sea coral. This is the result of generative design, a process where human engineers provide a set of constraints, heat dissipation requirements, weight limits, and structural load points, and an AI grows the part through millions of iterations of simulated evolution. This is the dawn of the inscrutable engine. Historical trends in aerospace have shown that these organic, lattice-based geometries can reduce weight by 40%, while increasing thermal efficiency by a factor of 3. However, the potential outcomes for the automotive repair industry are catastrophic. We have reached a point where the physical architecture of the car has moved beyond the processing power of the human visual cortex. Sam can put on the most advanced 3D training headset in the world, and he can see the 3D labels floating in space. The labels might tell him that a specific area of the lattice is a high-pressure bypass. But looking at the twisting, nonlinear, and fractal-like pathways of the metal, Sam's brain cannot read the logic of the machine. He cannot look at it and say, if this leaks here, the pressure will drop there. The logic is buried in fifth-dimensional fluid dynamics that only a supercomputer can calculate. Imagine if you were asked to repair a human circulatory system by hand. That is the level of complexity we are talking about in 2026. These generatively designed parts are often manufactured using high-speed 3D metal printing, meaning they have no seams, no fasteners, and no internal access points. They are unitary solids. If a single internal channel in that coral-like manifold becomes restricted by sediment, there is no way to clean it. There is no way to rebuild it. The 3D training system, which was designed to help technicians understand the machine, has now become a witness to the machine's total opacity. The training module simply displays a red translucent overlay and gives a single instruction: remove and recycle. This is the repairability singularity. It is the moment when the complexity of a machine exceeds the human ability to intervene at a granular level. Step by step, the transition to this state is driven by the pursuit of extreme efficiency. Step 1. The shift from mechanical valves to fluidic logic, where the shape of the tube itself directs the flow of coolant without any moving parts. Step 2. The integration of structural and functional components, where the car's frame also acts as its cooling system and its battery housing. Step 3. The total elimination of human serviceable interfaces. By the time we reach Step 3 in late 2026, the 3D training we've spent this masterclass discussing changes its fundamental purpose. It is no longer teaching Sam how to be a mechanic. It is teaching Sam how to be a specialized disposal technician. The impact on the dark repair movement and technicians like Riley in Nebraska is profound. How do you jailbreak a part that has no discernible internal logic? Riley can use his LiDAR scanners to rip the 3D geometry, but the resulting mesh is so complex that even his cracked AI models struggle to find the fault. This is the self-obfuscating machine. Manufacturers have realized that they don't need to use encryption to lock Riley out of the car. They just need to make the car so complex that no independent human can understand it without the manufacturer's proprietary inference engine, a specialized AI that interprets the chaotic geometry of the parts. Case studies from the 2025 rollout of Neuralink powertrains indicate that when a technician is forced to work on these systems, they experience a high level of cognitive dissonance. They are looking at a machine, but their instincts for how things work are constantly being triggered and then frustrated. Imagine if every time you turned a doorknob, the door opened by sliding into the floor. After a while, you stop trying to understand the door, you just turn the knob because the 3D goggles told you to. This leads to a total atrophy of mechanical intuition. In 2026, we are seeing the first generation of technicians who can perform a $300,000 repair on a hyper EV, but cannot tell you how a basic internal combustion engine works. They are masters of the interface but strangers to the metal. The depth of this chasm is further widened by the use of stress-mapped structural fusions. In a 2026 vehicle, the density of the metal in a single subframe can vary from point to point based on AI-calculated load paths. To the naked eye, the metal looks uniform, but in a 3D training overlay, Sam sees a psychedelic map of varying densities. If the car is involved in a minor collision, Sam cannot just straighten the frame. The internal lattice has been compromised in a way that is invisible even to X-rays. The 3D system calculates that the frame's structural integrity coefficient has dropped below the safety threshold. The car, through Sam's headset, essentially condemns itself. This leads to a massive increase in vehicle total loss rates, a trend that is already driving U.S. insurance premiums to record highs in 2026. But there is a final, even more unsettling development. We are starting to see the integration of live data feedback loops, where the vehicle's 3D digital twin is being updated in real time as the car drives. If Sam tries to install a mesh-approved third-party part, the vehicle's AI notices the microscopic change in thermal signature or vibration frequency within seconds. It doesn't just flag the part, it re-optimizes the rest of the engine to work around the unauthorized part, often causing the new part to wear out prematurely or operate at 20% efficiency. The machine is actively fighting the repair. It is a biological-style immune response translated into mechanical engineering. As Sam stands in his Detroit lab, he realizes that the era of the master tech is ending. He is no longer a surgeon. He is a witness. The 3D training suites are becoming so advanced that they are essentially doing the thinking for him, leaving him to provide only the physical labor of swapping modules. This is the ultimate open loop. If the machine is too complex for humans to understand, and the AI is the only thing that can diagnose it, then who is really in control of the American road? Are we moving toward a future where the car is a black box that we simply rent from a corporation until it decides to stop working? We have explored the headsets, the remote experts, the automated shops, and the 3D printed rebellions. But all of these topics have been leading to a singular, inevitable conclusion. We are at the doorstep of the final stage of this evolution. It is a stage where the training and the repair are no longer separate events, but a continuous, invisible process. In the final part of this masterclass, we are going to look at the universal grid, the point where every vehicle in the United States becomes a single, interconnected 3D organism. We will see how your car will fix itself while you sleep, how the very concept of a mechanic shop will vanish from the American landscape, and the one terrifying master key that could bring the entire system crashing down. If you think 3D auto repair is about fixing cars, you've only seen the surface. The final part of this series will show you what's really under the hood of the 21st century. We are going to the end of the road. To understand the end of the road, we have to look at the life of Maya in Arlington, Virginia. It is December 2026. Maya does not think about auto repair. She does not own a toolbox, she does not know the location of her nearest service center, and she has never seen a 3D diagnostic headset in person. Yet, her vehicle is the most perfectly maintained machine in the history of her family's lineage. This is because Maya's car is a live node in what is now called the Universal Repair Grid. In the previous 9 parts of this masterclass, we have tracked the evolution from the physical wrench to the digital ghost. Now we are witnessing the final integration, the point where the machine, the 3D data, and the infrastructure become a single self-healing organism. Imagine if your car was constantly being repaired while you were driving it. This is the reality of the 2026 Universal Grid. As Maya drives down I-66, her vehicle is communicating with the road surface and a localized mesh network of other vehicles. Every vibration, every thermal spike, and every millisecond of sensor latency is being fed into a collective 3D model. If Maya hits a pothole, the 3D system doesn't just log a suspension event. It compares the impact data against the 3D digital twins of 500 other vehicles that hit the same hole. The grid identifies that a specific strut in Maya's car has reached a fatigue threshold that will lead to a failure in exactly 412 miles. Historical trends in vehicle maintenance relied on reactive or preventative schedules, changing oil every 5,000 miles regardless of its condition. The potential outcomes of the universal grid are the total elimination of scheduled maintenance. Instead, we have moved to continuous precision upkeep. While Maya sleeps, a mobile 3D hub, an autonomous robotic van, is dispatched to her driveway. This hub is a miniature version of the automated bay we discussed in Part 6. It doesn't need a human driver or a human technician. It uses its own 3D sensors to locate Maya's car, deploys a robotic arm, and replaces the fatigue strut with a 3D printed modular component. Maya wakes up to a notification on her smart glasses. System optimized. The total cost was automatically deducted from her mobility subscription. No shop, no waiting, no human error. This leads us to the vanishing of the American shop. In 2026, the real estate once occupied by independent garages and massive dealership service bays is being repurposed into data centers and battery recycling hubs. Historical trends indicate that as the mean time to repair drops toward zero, the need for centralized physical infrastructure evaporates. The step-by-step breakdown of this shift is clear. Step 1. The standardization of 3D modular components that can be swapped by basic robotic actuators. Step 2. The deployment of autonomous mobile service units. Step 3. The transition of the mechanic from a local worker to a global 3D systems architect. But within this perfect system lies the master key, the single most dangerous vulnerability in the 21st century automotive landscape. To understand this, we have to look at a hypothetical but technically possible scenario in the year 2026. A spatial injection attack. Because every vehicle is relying on the same centralized 3D master files for their digital twins, a single corruption at the source could have a cascading effect. Imagine if a malicious actor gains access to the 3D geometry file for a common brake actuator used in 10 million vehicles. By subtly altering the 3D coordinates of the closed position by just 2 millimeters in the master file, the attacker could effectively disable the physical braking capability of an entire nation's fleet simultaneously. The 3D data is no longer just a training tool. It is the source of truth for the physical world. If the 3D map says the bolt is tightened, the robotic hub believes it. If the 3D map says the sensor is calibrated, the car trusts it. We are moving into an era of cybermechanical warfare. Case studies from 2025 regarding ghost faults in logistics fleets have shown that when 3D data is tampered with, the human eye cannot detect the error because the machine is behaving exactly as its 3D instructions dictate. This is why the final job of the human element in 2026 is the role of the 3D forensic auditor. These auditors are the elite descendants of the master technicians we met in Part 1. They don't fix cars, they fix the data that fixes the cars. They spend their days inside high-fidelity VR environments, walking through the 3D code of millions of repairs, looking for anomalies or spatial hallucinations, where the AI has hallucinated a repair that didn't actually happen. They are the last line of defense between a functioning society and a total mechanical collapse. Historical trends in cybersecurity suggest that as our machines become more intelligent, our primary risk shifts from mechanical wear and tear to algorithmic corruption. The depth of this transition is hard to overstate. We have moved from a world where you could fix your car with a hammer and a prayer to a world where your car is a temporary physical manifestation of a cloud-based 3D model. The economic potential for the United States is a radical increase in logistics efficiency and a decrease in the total cost of transport. But the cost is the total loss of the analog individual. In 2026, if you want to work on your own car, you aren't just fighting a bolt. You are fighting a global network of 3D verification protocols. Let us look at a final case study involving a classic car enthusiast in Tennessee. He owns a 2015 internal combustion truck, a dinosaur in the eyes of the 2026 grid. Because his truck doesn't have a 3D digital twin and cannot communicate with the universal grid, it is being slowly regulated off the road. Insurance companies refuse to cover it because its repairability coefficient is too low. This is the hidden side of the 3D revolution, the exclusion of the non-digital. The future of mechanic training has reached its logical conclusion. It has trained the human out of the loop entirely, leaving us with a world of perfect machines that we no longer truly understand or control. As we conclude this deep dive masterclass, we have to ask, what is the next frontier? We have conquered the 3D space of the individual vehicle. We have automated the shop. We have decentralized the repair. But as Maya's car drives itself silently through the Virginia night, a new shadow is beginning to form on the horizon of 2027. We are seeing the first signs of molecular repair, technology that doesn't just swap parts, but uses nanotechnology to regrow metal and plastic in real time. The 3D map is getting smaller, moving from the component level to the atomic level. The era of 3D auto repair was just the beginning of the end of the mechanical age. We are now entering the age of the programmable matter vehicle. If you thought the empty shop was a radical change, you have no idea what happens when the car itself becomes a living, breathing, and thinking material. In our next masterclass series, we will dive into the nanomechanic and the rise of the biosynthetic fleet. The road doesn't end here. It just changes state. Stay tuned as we prepare to look into the microscopic future of the American road. The wrench is dead. The 3D model is king. But the atom is coming for the crown. Would you like me to begin the research for the molecular repair series?